Module 5, Blockchain Security and Digital Identity. Lecture 2, Smart Contract Security. In this lecture, we will cover the following topics. Specific security considerations of smart contracts. Best practices. Review of biggest smart contract exploits. Sources for future research. This lecture is part of Module 5, Blockchain Security and Digital Identity. With this lecture, you're going to learn how to examine specifics of smart contract security compared to the traditional software security. Examine smart contract security best practices. Analyze the biggest smart contract exploits to date. The minimum requirements for this lecture are familiarity with basic Solidity syntax and programming, basic understanding of transaction execution sequence in EVM, ability to use CLI to run commands, familiarity with EVM wallets, example, MetaMask, MEW Wallet, or Brave Wallet. Specific security considerations of smart contracts. Immutability is one of the core functionalities of blockchain technology. It provides one of the most important security aspects of the technology while also impacting smart contract security in a significant way. Any information added to the blockchain cannot be changed post-fact, meaning that any smart contracts can't be updated as well. Block hashes represent the hashed value of the block content as well as the block hash of the previous block, effectively chaining all of the blocks and the information within them into an unbreakable series of hashes. Any change to the content of an existing block is easy to detect as the hash of the block would change, breaking the chain of hashes and invalidating it. This ensures the trust component of the blockchain. How does this apply to smart contract security? The smart contract code written to the chain cannot be changed. Any vulnerabilities are permanently added to the chain. Smart contract code is stored in a block it was deployed to. Updating the code of a deployed smart contract would require changing the code in an existing block already included in the chain. A vulnerable smart contract deployed to a blockchain represents a permanent security vulnerability. The longer such a smart contract is being used, the higher the possibility that someone discovers the vulnerability and exploits it. How does this apply to smart contract security? The inability to update the smart contract without breaking the chain of hashes makes it impossible to fix the security vulnerabilities that are already deployed. Smart contracts are accessible to anyone connected to the blockchain. Anyone can find the bytecode deployed to the chain, the transactions related to it, and the events the smart contract emits. The smart contracts can often be verified, providing the source code in a human-readable format, and if they are not, the bytecode can be decompiled to provide one. Sending transactions to any address is permitted in the blockchain network, so anyone can try to interact with a deployed smart contract. Unless governed by access control, any function of the smart contract can be called by anyone. Since anyone can try to interact with a deployed smart contract, anyone can try to call any function and search for security vulnerabilities. How does this apply to smart contract security? The ability for anyone to call the functions in the smart contract provides the risk of anyone being an attacker. Smart contracts execute in the EVM Ethereum virtual machine. There is more than one variation of the EVM available. Originally there was the only one used in the Ethereum network. As more and more blockchain networks appear, more and more variations of EVM appear as well. Some only change simple parameters, while others rebuild their EVM from the ground up. The EVM determines the constraints of the smart contracts. Gas consumption of actions. Each action in the execution of a function call has a predetermined gas requirement. The sum of all actions gas requirements results in the transaction gas requirement. Gas limit of the transactions. Each block in a blockchain has a predetermined maximum gas allowed. A transaction cannot consume more than the maximum amount of gas. Surpassing the allowed gas maximum of a block results in a failed transaction. Smart contract file size. In addition to the gas limit of the block, the smart contract file size is also limited. While the gas limit isn't breached by storing larger files, this safeguards the chain data from bloating over an unmanageable size. Inability to access the Internet. As a blockchain network is a completely separate network from the Internet, this means that any resources that would be available to conventional applications are natively inaccessible to smart contracts. Without the ability to access centralized information databases, smart contracts must rely on the data stored within them or on the one being passed to them by users. How does this apply to smart contract security? As the EVM can be updated, the constraints of the smart contract execution can change. This can also impact their functionality. Limiting gas available for calls executed by the smart contract allows for the prevention of unauthorized forwarded calls. For example, a malicious smart contract could pose as having a legitimate method available to the user, but really forward their call to perform a malicious action. Redefinition of the gas cost of opcodes can alter the required gas of a call. For example, address.send method was used to work for smart contracts used for forwarding funds sent to them, but the gas consumption of such smart contracts rose through the .send method's threshold after the opcode gas requirement redefinition. How does this apply to smart contract security? Relying on methods with a hard-coded gas limit may improve the security of the smart contract, but might also make it unusable should EVM constraints change. Access control refers to the definition of who is allowed to call which function of the smart contract. As each function of the smart contract is reachable by anyone connected to the network, access control is very important. Some functions control the operation of the smart contract, while others control the assets held by the smart contract. Some smart token contracts, like ERC20, ERC721, and ERC1155, have the ability to create or mint new tokens. Exposing the ability to do so to the public would completely invalidate the token. Some smart contracts implement the self-destruct mechanic. Abusing it would result in complete disruption in its operation. How does this apply to smart contract security? If a function that controls the operation or assets is compromised, the smart contract itself is compromised. Correctly implemented access control can protect the management and asset functions, but that might not be enough. DAOs, decentralized autonomous organizations, depend on decentralized governance. This means that all of the members have a say in how the DAO evolves. Attaining membership and voting power has to be carefully thought out. Otherwise, the DAO can be hijacked or abused by the attacker. Failure to properly safeguard against governance attack can result in a complete loss of funds or value of the DAO. How does this apply to smart contract security? Governance designed in a way that it is possible to be abused makes for a common attack vector. Smart Contract Weakness Classification. Smart Contract Weakness Classification, SWC, provides a well-documented public software weakness classification scheme. There are several benefits of SWC. It defines a straightforward way to classify weaknesses in smart contract systems. It defines a straightforward way to identify the weaknesses that lead to vulnerabilities in smart contract systems. It defines a common language for describing weaknesses in smart contract systems architecture, design, and code. It trains and increases the performance of smart contract security analysis tools. How does this apply to smart contract security? Properly defined common weaknesses can help avoid common security pitfalls in smart contract development. Familiarity with common SWCs can help us avoid common security vulnerabilities of smart contracts. These are some examples of the common smart contract-related weaknesses. SWC 115, Authorization through TX.origin. Executing access control based on the origin of a transaction rather than the sender of the message is dangerous because it could lead to the call forwarding exploit. The transaction forward exploit refers to a malicious contract tricking a user into interacting with it and then calling the attacked smart contract, with the transaction origin being the tricked user. SWC 105, Unprotected Ether Withdrawal. Improper implementation of Ether withdrawal can lead to the exploiter draining the smart contract. Without proper protection, an Ether withdrawal from the smart contract can be exploited using a reentrant call to drain the smart contract of all of its funds. SWC 103, Floating Pragma. If a compiler is not explicitly defined, a version other than the one that was used to develop and test the smart contracts can be used. This can result in unexpected behavior of smart contracts. Familiarity with common SWCs can help us avoid common security vulnerabilities of smart contracts. These are more examples of the common smart contract-related weaknesses. SWC 136, Unencrypted Private Data on-chain. Even if there is no convenient getter function to read the value of a private variable, this does not hide their values. This has the potential to reveal sensitive information to an attacker. A variable value stored in a public blockchain network is included in the chain code. This means that anyone with sufficient knowledge can access and read it. SWC 128, Denial of Service with Blocked Gas Limit. Programming patterns that are harmless in centralized applications can lead to denial of service (DOS) conditions in smart contracts when the cost of executing a function exceeds the blocked gas limit. Implementing an ever-expanding array of values would allow the attacker to expand it over the limit, causing any transaction initiated by a legitimate user to fail. Best practices. Using battle-tested and properly reviewed code allows us to minimize the risk of introducing our own security vulnerabilities. Battle-tested code has been used in many existing decentralized applications and has probably evolved through time to be as resilient to attacks as possible. Most of the ERC implementations are available in this form and included in smart contract development packages. Using smart contract development packages allows us to include such smart contracts in our own solution and streamlines the development by only requiring us to develop the custom business logic. It is important to review the documentation of the battle-tested code to ensure it is properly included in the smart contract. Documentation of smart contracts includes instructions on how to properly initialize and integrate them in our own smart contracts and provides a list of guidelines and limitations incurred by using them. How does this apply to smart contract security? Using battle-tested and reviewed code reduces the risk of introducing unnecessary bugs to smart contracts. Using a battle-tested ERC-20 implementation instead of writing our own ensures that we don't forget to make sure that only the owner of the tokens is allowed to manage them. A vulnerability allowing random users to manage others' tokens would result in balances being drained. Using a battle-tested ERC-173 implementation instead of writing our own ensures that the ownership role of the smart contract can only be transferred by the intended actor. Allowing others to transfer the owner role could mean that your smart contract would be hijacked. Using a battle-tested ERC 1167 implementation instead of writing our own makes sure that the proxy smart contract uses as little gas as possible. Spending more gas than intended could result in the transaction being reverted due to it running out of gas. How does this apply to smart contract security? Implementing standardized battle-hardened code assures that security vulnerabilities have been removed from it through numerous discussions and experiences. Only one account holding all of the management and maintenance power introduces a security vulnerability. If that account is compromised, this means that the smart contract is compromised as well. Separating access control between multiple accounts, each in charge of a part of a smart contract, reduces this risk. For example, if the account in charge of setting the list of user accounts able to interact with our smart contract gets compromised, other management accounts can revoke its access permission and instantiate a new account with such permissions. Defining distinct levels and tasks of access control also makes the management more transparent. Clearly defining levels and tasks of access control allows for greater transparency of who can initiate what action and makes it easier for potentially malicious accounts to be held accountable for their actions. How does this apply to smart contract security? As the management and maintenance functions can make or break smart contracts, it is important to sufficiently protect them using access control. Testing is an integral part of all software development. Testing can validate the expected behavior of smart contracts. Any derivations from the expected behavior mean there has been an error while implementing the business logic. Testing can catch any missed implementations in the business logic of smart contracts. Changes to the smart contracts can be validated to not impact the expected behavior with extensive test suites. As testing is usually done in a local environment, tests are not limited with gas consumption and can be gas-intensive as the transactions are free. How does this apply to smart contract security? Validating both the happy and sad flows of smart contracts can catch the potential vulnerabilities of business logic in smart contracts. Extensive test suites can also safeguard smart contracts from new security vulnerabilities introduced by future modifications of the code. Even the dedicated design of a smart contract can implement some of the SWCs. Static analysis of the smart contract for the SWCs can reveal the unintended behaviors implemented within them. However, some SWC violations may need to be implemented by design. Such an example is the Smart Contract Tunneling (SCT), which uses tx.origin, violation of SWC 115, as well as message sender to establish secure tunnels between smart contracts. How does this apply to smart contract security? Making a conscious decision to fix or keep an SWC violation in a smart contract means that we are aware of potential security risks included in the smart contract and accept them. Bounties are awarded for responsibly reporting a security vulnerability once it is discovered. Responsible reporting of a security vulnerability includes description, implications, and reproduction steps. The more detail is provided, the easier the vulnerability is to address. It should be communicated with the maintainer of the smart contract in a confidential way before being disclosed to the public after a grace period. Confidentially communicating the potential vulnerability with the maintainer allows them to address the issue before a malicious actor exploits it. Publicly posting the vulnerability details after a clearly communicated grace period assures that the maintainer is motivated to fix the vulnerability as soon as possible. Bounties can either be managed by the maintainers of the smart contracts or by services dedicated to bounties. Bounties are usually defined by the level of severity they represent and should be posted publicly and accessible to all. How does this apply to smart contract security? Sufficient bounties might sway a potential attacker to disclose the security vulnerability rather than exploit it for their own gain. Review of biggest exploits. The target was a decentralized venture capital fund where investments were based on community votes. The exploit was executed by abusing the incorrect setting of the function, where execution of the call came before the check on whether the call had already been executed or not. This opened up the smart contract for a reentrancy attack. When the funds were transferred out to the malicious smart contract, it recursively called the same function and drained the original smart contract. 3.6 million Ether was stolen. How does this apply to smart contract security? Making sure that the order of statements within each function adheres to the best practices outlined in the documentation would prevent such an exploit. Implementing a reentrancy protection coding pattern is a common good practice to avoid similar exploits. The target was a company designing and maintaining the Polkadot ecosystem. In the early days, they designed a multi-signature wallet smart contract with a bug that allowed exploiters to obtain 150,000 Ether. A group of white-hat hackers managed to use the same exploit to save an additional 377,000 Ether that was later distributed back to the original owners. The source code had been reviewed by a Solidity expert, but the bug was included after the review in one of the updates. How does this apply to smart contract security? Implementing clearly defined deployment and review practices could have caught the faulty addition of the code and prevented the exploit from being added to the smart contracts. The target was a bridging protocol that allows users to transfer funds from one blockchain network to another. The exploit happened in the bridge between Ethereum and Solana network on Solana's side. Exploiter managed to mint 120,000 unbacked wrapped Ether. How does this apply to smart contract security? The Solana smart contract had to be rewritten in Rust programming language and was audited prior to the exploit. Extensive end-to-end test suites are required to catch such a deeply rooted vulnerability. The target was the Ethereum sidechain used for Axie Infinity game. 5 out of 9 validator private keys were stolen, giving the attacker absolute control over the protocol. 4 of the keys were owned by the developer of the game. The last key was exploited by an already discontinued allow list that was not revoked. Allow list was used to allow the developer of the game to validate transactions in place of the owner of this validator. Exploiter was able to drain 173,600 wrapped Ether as well as 5 million USDC stablecoin. How does this apply to smart contract security? Private keys, as well as all of the sensitive data, should be kept extremely confidential and in line with all of the best security practices. All of the exceptions to the best security practices, like allow lists, should be revoked and removed as soon as they are not needed anymore. The target was the interoperability protocol, connecting various blockchains. The term protocol is used to address a set of smart contracts providing a unified service to the users. Vulnerabilities in the network's contract call used to power the protocol were exploited by overriding the instructions to divert the funds to 3 wallets. Contract calls are analogous to Ethereum's transactions. In the attack, $611 million in various cryptocurrencies were stolen. Most of the funds have already been returned following successful communication with the exploiter. How does this apply to smart contract security? Best security practices would reduce the likelihood of the exploit. Fortunately, the response of the maintainers was swift, and the offer of a significant bounty, as well as quickly reaching out to the exploiter, saved most of the funds. Sources for future research. Thank you for listening to this lecture.